Okay, let's just dive right into this. Welcome to today's explainer, Modeling the Chaos, Inside T10 Cricket Predictions. You know, if you've ever watched a live cricket match and seen that little win probability graphic ticking up and down on your screen, you might think it's just a simple math formula running in the background. But to power that graphic, as we're going to see today by looking at Cricmetric's production model, requires an incredibly complex, lightning-fast artificial intelligence.
And we aren't just talking about regular cricket here. We're talking about T10 cricket. For those of you who follow it, you already know T10 is pure, unadulterated chaos. A full match is completely finished in barely 90 minutes. It's an absolute sprint. So the big question we're exploring today is, how exactly does the math keep up with that level of madness? How do you build a machine that instantly understands a game moving at warp speed?
Well, the core of that challenge really comes down to one number, 120. In a T10 match, there are only 120 legal deliveries. That's it, the whole game. In longer formats, a batting team can take an over or two to just, settle in, assess the pitch, and slowly build a partnership. But in T10, that luxury simply does not exist. Every single ball is an event. Every single delivery carries massive weight.
And that on-field chaos is perfectly mirrored in the data. Think about the crazy sharp spikes in win probability you might see during a tense match between the Quetta Cavalieri and the UAE Bulls. In T10, a single over with a couple of big sixes and a crucial wicket can swing a team's chances from a super comfortable 80% down to a panic-inducing 20% in the blink of an eye. The data is entirely nonlinear. Scoring 10 runs when you have 9 wickets in hand means something completely different than scoring those exact same 10 runs with only 1 wicket left.
So to capture those massive, nonlinear swings, simple historical averages or basic statistical models just don't cut it anymore. Enter the technological hero of our explainer. It's called XGBoost, which stands for Extreme Gradient Boosting. Now, I know that sounds like a sci-fi rocket thruster, but it's actually the machine learning algorithm that serves as the prediction engine for Cricmetric. And honestly, don't think of XGBoost as this cold, complex black box. Instead, I want you to picture a panel of 1,000 highly opinionated cricket analysts sitting in a massive room running a rapid-fire relay race. The first analyst looks at historical T10 data and guesses who's going to win. The second analyst steps up but looks only at where the first one made a mistake and adjusts the prediction. Then the third zeroes in on the second's errors and so on. This ruthless cycle of correction happens 1,000 times in fractions of a second, resulting in a highly dynamic engine that reacts to every single delivery.
But, there's always a catch with AI. If you just throw raw match data at a standard machine learning model, it will sometimes completely ignore the laws of physics, or at least the fundamental laws of cricket. For example, raw AI might look at a weird historical outlier where a team lost a wicket but still somehow won, and it might conclude that losing a wicket actually increases your chances of winning. Obviously, if a broadcaster put that nonsensical math on live TV, fans would absolutely riot. We need a common sense model.
To solve this, developers use something called Monotone Constraints. Basically, they hard-code cricket common sense directly into the AI's brain. So for the batting team, scoring runs absolutely must increase win probability, while losing wickets or consuming balls has to decrease it. For the chasing team, the exact opposite applies. By locking in these non-negotiable guardrails, the model is forced to behave logically. Even if it encounters a bizarre, extreme scenario it has literally never seen before in the historical data.
Okay, so with those common sense rules firmly in place, the AI handles the live action beautifully. But that brings us to what's probably the trickiest part of a 2-innings win probability model. What on earth happens at the innings break? How does the math transition smoothly from tracking the team setting the total over to the team chasing the total?
Think about it like this. Imagine Team A finishes their 10 overs at 115 for 4. In that exact split second, the second inning begins, and Team B needs 116 to win. If the system uses 2 completely separate models, one for the first inning and one for the second, you'd get an embarrassing broadcast glitch. The first inning model might say Team A has a 55% chance of winning right as they walk off the pitch. But the instant the second model turns on, it calculates Team B has a 48% chance, which suddenly implies Team A dropped to 52%. The graphic would just abruptly jump, while absolutely no cricket is even being played.
To fix this logic gap, Cricmetric built a brilliant consistency override. I like to think of it as a mathematical handshake. At the very last ball of the first inning, the model steps in and enforces this strict rule. The probability of Team A winning right now must exactly equal 1 minus the probability of Team B chasing down this exact target in the second inning. This handshake perfectly bridges the two models. It locks the odds seamlessly in place during the break, so viewers at home don't see any jarring, inexplicable jumps in the numbers.
And this underlying logic also extends to projecting the actual final score. Most basic score predictors just give you a flat, boring number on the screen, like projected score 105. But any cricket fan knows that early on in a 10 game, the range of possibilities is just massive. So instead of spitting out a single, potentially misleading number, this engine uses a separate volatility model to estimate that massive uncertainty. They actually call this the fog of war.
And it's fascinating how that fog of war slowly lifts as the match goes on. At over 2, the model might project a final score of 110. But because the game just started, the cone of probability is huge. It could be anywhere from 85 to 135. By over 8, the projection might still be 110, but the data has tightened significantly to a range of 102 to 118. Finally, at over 10, that boundary collapses entirely to the exact final score. It doesn't just blindly tell the viewer what's likely. It mathematically measures the exact unpredictability of the game in real time.
So behind that incredibly clean, simple graphic on your TV screen is a stunning symphony of tech, high-speed machine learning, strict hard-coded cricket logic, seamless mathematical handshakes, and real-time uncertainty tracking. Next time you see that win probability needle swing wildly after a dramatic double wicket over, just picture those 1,000 invisible digital analysts relentlessly crunching the numbers. And it really makes you wonder, as sports and data become even more deeply intertwined, what entirely unpredictable elements of the game are these AI models going to decode next?